So welcome to those of you watching on catch up on our YouTube channel. We're going to be looking at acids and alkalis today. A reminder of the times that we're suggesting that you do some of the work we're going to talk about. The work is going to be this week, as well as this webinar, is there's going to be a Google quiz as usual, but we're going to be asking you to have a go at some home experiments if you can. It's using things which are either very cheap or you can pick up from the shops. Knowing about this on Monday, it gives you time to prepare for Wednesday or Thursday. Those of you who might be in school, Miss Wanstall is going to see if she can arrange something either on Wednesday or Friday when she is in school. So more details coming to you about that. But we're going to start by warming up, thinking back to what we were looking about exothermic and endothermic before. So 3 quick polls on exothermic and endothermic. So get your poll fingers ready. First poll. What does it mean for a reaction to be endothermic? 3 options there. Choose the one that you think is the correct option. Endothermic, exothermic. The way I like to think about this is if you're going out of a room, you're going out of the exit. So if you're giving out heat, then you are exothermic. Whereas if you're taking in heat from the surroundings, then you are endo. It doesn't quite work, but it's kind of works. Endothermic. Okay, let's have a look, show you guys that. Good, 81% of you remembering that. Good job, guys. Let's have the next question about exothermic and endothermic. This is about bonds. So when bonds are broken, energy is, what happens to the energy? Okay, so we've got a bond, here's my bond, and it's a strong bond. If I want to break this bond, what have I got to do to the bond? Here's the bond, I want to break the bond, but it's really hard. I've got to do something with energy. What is it? Good, lots of you voting. And with a little bit of an explanation, okay, it is taken in. So when you break a bond, you've got to put energy in. Some of you are saying energy is created. Remember, one of the laws of energy can't be created, can't be destroyed. It just gets turned from one form into another. Here it's getting turned from thermal energy in the surroundings into potential energy, chemical potential energy in the chemicals. So it is taken in. And you see there, just over half of you got that right, but with a little bit of reminder and explanation, hopefully this next poll, you guys are going to get much higher. So what about when bonds are made? When things come together, when bonds are made, what happens to the energy? Okay, fantastic. Lots of you much quicker on the draw here. You've got your heads around it, woken up a bit, had a cup of coffee maybe. Good, right? So when those bonds are made, when you're making a bond, it gives out energy. So you can see here, 89% of you got your heads around it, getting back into gear. Good job. So there you go, 89%. Some people still saying created or destroyed, just a few of you. Remember, energy cannot be created, energy cannot be destroyed. Not possible. Well, let's not get into that. Cool. Okay, but what we're going to be talking about today is acids and alkalis. So the first thing I want you to do, again, a bit of a warm-up. Which of these is a fake acid, is not the name of a real acid? Some of you might get the reference. Go back. Spot the fake acid. Which of these is not a real acid? Some of you might spot the reference there. There's a Rick and Morty episode with a vat of fake acid. Which of these do you think is not the name of an acid that is a real acid that you might come across either in a lab or maybe in your house? Hydrochloric acid, acetic acid, citric acid, atazoic acid, sulfuric acid, nitric acid. One of those I made up. And looks like most of you have spotted which one? Atazoic acid, no such thing as atazoic. You can get benzenoic acid, that's kind of fun. But hydrochloric acid, that's the acid you get in your stomach. Acetic acid, that is also sometimes known as ethanoic acid, and that's the acid that's in vinegar. So you've probably got some of that in your house. Citric acid, that's the acid that's in citrus fruits. So that's really common acid in people's houses. If you've got a lemon or an orange hanging around in your house, it's got citric acid in it. Sulfuric acid is a less common acid, so is nitric acid. But I've included those two because there are 3 acids that you just have to learn for the purposes of the GCSE. These are the ones that the exam board say you have to know these 3 acids. So they can just ask you straight up, what is the formula for nitric acid? They could ask you a question like that, which would be like a 1-mark question, or they could do it as part of a bigger question where they assume you know the formula for nitric acid in order to help answer the question. So these are 3 that you've just got to learn. Hydrochloric acid is HCl, 1 hydrogen, 1 chlorine. Now this might look a bit like an I here, but that is a lowercase l. Remember, when we're doing chemical formulae, if there's 2 letters, the first letter is always a capital, the second letter is a lowercase. So this is a capital C, a lowercase l for a chlorine atom. Over here, by contrast, that's a capital S and that's a capital O. So those are separate atoms. This is sulfuric acid, H2SO4. So 2 hydrogens, 1 sulfur, 4 oxygens. And nitric acid is HNO3, again, capital N, capital O, they're separate atoms. So we've got 1 hydrogen, 1 nitrogen, and 3 oxygens. Now you'll notice something that is the same about all of these acids. They all have hydrogen in. Now we're going to come on to that in a minute. Now, we did teach you about acids and alkalis back in year 7. So a little bit here to remind you, we're going to have a quick reminder about the pH scale. Now, I've taken off all the labels and I've taken off all the colors. So this is just a straight memory test back from year 7. So if I have something that is a weak acid on this pH scale, what might be its pH for a weak acid? So we've got this scale from 1 to 14. If it's a weak acid, where's it likely to be roughly on this scale? Okay, good. Lots of you voting. Fantastic. And gonna call it there. And loads of you, about 2/3 of you have remembered, yeah, weak acid, it's going to be around about 5. Maybe it could be 4, maybe it could be 6. But this kind of area, this is the acidic side. Less than 7, that's the acidic side. And as you go further across it, you get stronger and stronger and stronger acids. Now, we're going to dig into what exactly that means a bit later. But you've got that. Good job. So what about then if something is a strong alkali? Where would that be on my pH scale? Lots of you voting and voting really quickly now. Again, maybe this is coming back to you. And much better results. Yep. So 86% of you getting it right down this far end, pH 14. This side of 7 is the alkali side. And again, close to 7 is weak alkalis. Further you go from 7, the stronger the alkalis gets. 14 would be a very, very strong alkali. So last one on this before we move on. What about if I've got something that's neutral? What would its pH be? Now you'll notice I say not what might it be. There is one correct answer for this. A weak acid could have been 4, 5, or 6, but for something to be neutral, really pleased to see nearly all of you getting it right. There's only one person who hasn't, and I expect that might have been a misclick. pH 7. If something is very slightly more than pH 7, let's say pH 7.1, then it's an alkali. If it's very slightly less than 7, let's say 6.9, it's an acid. It has to be exactly 7 for it to be neutral. So here we've got this idea that anything less than 7 is an acid. The strong ones are down here. The weak ones are here. Anything which is more than 7 is an alkali. The weak ones are 8, 9. Strong ones are higher up here. That's going to bring me on to indicators. So again, something that we touched on in year 7, but what can you remember about indicators in this topic? What is an indicator? Is it a light on a car that tells you if you're turning left or right, an instrument that's used to measure pH, a chemical that changes color in different pHs, or a logarithmic scale for the ratio of H+ to OH- ions? Ah, I'm surprised. Nobody is choosing the light on the car that tells you if it's turning left or right. That is called an indicator. It's technically right. And I thought some of you would go, well, actually, sir. But no, good. You're all taking this seriously. Good job. So one person, finally, thank you. So most of you, 73% of you remembering, so an indicator is a chemical which changes colors in different pHs. And that can be really useful for telling us what the pH of a substance that we want to investigate is. So let's go and look quickly at indicators. Here's the pH scale with what's the main indicator we tend to use is universal indicator. And you can see universal indicator, here's the pH scale, goes from 0, sometimes the pH scale can go down to 0. We'll talk about that in a second, about what that might mean, up to 14. And it's got this amazing rainbow of different colors. It's a mixture of different compounds which are all different indicators that change color based on the pH. And universal indicator is probably the best indicator because it can tell you not just if something's an acid or an alkali, but if it's a strong acid or a weak acid or where it sits on the pH scale. So it's a really good indicator, and it's called universal because it can be used universally in all kinds of different situations. So good job. Lots of you remembering that. There are, of course, other kinds of indicators. So here's that same pH scale from 0 up to 14. And there are other kind of indicators. And that's something that we're going to be asking you to do in the work we're asking you to do, is maybe making some of your own indicators and doing those at home in a safe way. Ms. Wanstall will be talking to you more about that later. Okay. A couple more indicators then, just to show you that these aren't universal indicators. Red and blue litmus paper. Now, this is the same chemical, but in red litmus paper, when they make it, they add an acid in there to make it go red. And in blue litmus paper, they put a little bit of alkali in there to make it go blue. So then when you put it into an alkali, the alkali makes the red litmus paper go blue, and the acid makes the blue litmus paper go red. Now, that can't tell you whether it's a strong or a weak acid, simply whether it's acidic or alkali. So you can see that this might be useful. Just if I want to know, is this acid or alkali, I can check it, but it doesn't tell you whether it's that strong, sort of down at pH 1, pH 0, if it's a strong acid, or if it's more like pH 5, pH 6, if it's a weak acid. All it tells you is it's acidic. So useful, but maybe not as useful as a universal indicator. Another indicator that you will get familiar with is called, it's got an amazing name for Scrabble, phenolphthalein is how you say that, phenolphthalein. And phenolphthalein is, again, it's not a particularly sensitive indicator. It can't tell you whether it's a strong or a weak acid or a strong or a weak alkali, but it has got this really clear, really stark color change. When it's in acid, it's colorless, it's transparent and clear like water, but the words that we want to use in science for that is colorless rather than clear or transparent. So it's colorless in an acid, and it's got this amazing pink color when it's in an alkali. Now, that's going to be really useful when we get on to looking at something called titration. So I want to make you aware of this indicator because it's something that we will be using when we get back into school and start doing experiments. Okay, so we've got this other kind of indicator which can tell us whether something's an acid or an alkali. But I want to go back and look in a bit more detail about what it is to be an acid. Now, you might remember all of these acids, we said the thing that's the same about them is they all have hydrogen in. Well, lots of things have got hydrogen in. Water's got hydrogen in, but that's not an acid. That's neutral. So what is it that makes something an acid? It's got to have hydrogen in, that's definitely part of it, but it's about forming hydrogen ions. Normally, it's when it's dissolved in water. When you dissolve something in water, if it gives off hydrogen ions, H+ ions, then that makes it, that's what an acid is. And if there's lots of hydrogen ions available, then you get lower and lower down on the pH scale. And in fact, that's what pH stands for. The P stands for potential, and the H stands for hydrogen. And that's why the H in pH is a capital, because it's about these hydrogen ions. Now, it's slightly weird, you might think, because you might think if we've got lots of hydrogen ions, then shouldn't that have a really high number? It's the other way around in the pH scale. And again, we're going to dig into that in a little bit more detail. So if being an acid is about having hydrogen ions, what is it that being an alkali is about? And that is hydroxide ion. So this is an ion which contains one oxygen and one hydrogen, and it has a negative charge. It's gained one electron, so it's now got a negative charge. So these hydroxide ions are what makes something an alkali. So some really simple examples here of acids. We've already named some acids, but here are some examples of some alkalis. Hydrochloric acid, we talked about sulfuric acid, nitric acid. But have a look, here are some alkalis: sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, barium hydroxide. I think you're getting the picture. If it's got hydroxide ions in it, when it's dissolved in water, that's what makes it an alkali. So these H plus and OH minus ions are key to understanding what acids and alkalis are all about. And we will go into more detail about how they interact and like reactions with acids at another time. We haven't got loads of time to do that today, so we're not going to. Okay, hazard symbols you might see. This is, if it's a mild hazard, you get this exclamation mark. If it's a strong acid or a strong alkali, you might get this one, which means corrosive. If you put it on materials or on skin, it will react and corrode. There is another thing, though, as well as alkalis, called a base. And this can be confusing for students sometimes because they sound really similar. Both acids and alkalis, alkalis and bases react with acids. And they react with acids to neutralize them. So often you talk about acids and alkalis neutralizing each other. Well, an acid and a base will also neutralize each other. But there is a difference between a base and an alkali. Both bases and alkalis neutralize acids, but bases don't produce those OH minus ions when dissolved in water. So a really good example of this would be something like chalk or marble, something that's made of calcium carbonate. That calcium carbonate does neutralize acids. You put an acid on calcium carbonate and the acid will get neutralized. But if you put that calcium carbonate in water, it doesn't release those OH minus ions that you need to be an alkali. So bases are things that will neutralize acids, but don't necessarily form OH minus ions when dissolved in water. So here's a little Venn diagram to try and make it clearer. Here's a Venn diagram containing all the things that are bases, all the things that will neutralize an acid. But alkalis are a smaller subset of bases. They do neutralize acids, but they don't. They also dissolve in water to form OH minus ions. So all alkalis are bases, but not all bases are alkalis. Something like I said, like calcium carbonate, chalk, marble, doesn't dissolve in water to form OH minus ions. Therefore, it's not an alkali. It does neutralize acids, so it is a base. So something like, calcium carbonate would sit here in the Venn diagram. Something like sodium hydroxide does neutralize acids, and it does dissolve in water to form OH minus ions, so it's an alkali. Brilliant. So a quick recap then. The presence of which ion makes an acid an acid? What is it that makes something an acid? Okay, good job. Most of you clear on that. 91%, no, it's an H plus ion. Good job. And then what about then, what ion is it that makes an alkali an alkali? Good, really good. Loads of you coming in with the correct answer. This is such a key thing, and it's really important you get your head around it. It's why I'm really stressing it now. Okay, but we've got 93% of you knowing that alkalis, it's the OH minus ion that makes it an alkali. Good job. Right, I want to talk quickly then about strong and weak acids. So we've looked on the pH scale about what strong and weak acids are, and we've looked about acids. We're just going to focus on acids for a second, but the same is true for alkalis, just with OH minus ions instead of H plus ions. So the difference between a strong and a weak acid is when you dissolve it in water, is how separated does that hydrogen get? We know all acids have got hydrogen ions, and the hydrogen ions separate when you dissolve in water. The word we use for that is dissociate. So if you imagine looking at this picture here, here is the compound before it got dissolved. We've got the yellow hydrogen and the red, whatever it might be, the nitrate or the sulfate or the chloride ion or whatever it could be, the citrate. You can see when we've dissolved this in water, some of the hydrogens have got separated from the other part of that compound. They've disassociated, but not all of them. Look, some of them have stuck around. Whereas in a strong acid, they have completely or fully disassociated. All of those hydrogens have separated away from the non-hydrogen part of that compound. Now, the way I kind of think about this sometimes is thinking about when you end a relationship. Like when you end a relationship, sometimes it's a really like big, massive, acrimonious bust up. And you're like, I never want to see that person again. I'm never going to talk to them. And you completely separate from them and you never have anything to do with them ever again. Well, that's what a strong acid is. Look, they're completely separated. They're going their own ways and getting on with their lives. Whereas a weak acid or an alkali might be a relationship where, you know, you break up, but you stay friends. Maybe you've got the same friends and you just kind of see each other, and maybe you accidentally get back together again and then break up again. You're not completely separated. You're sort of a bit together, but you're apart, but you're maybe a bit together still, and it's a bit unclear and fuzzy. That's what a weak acid or an alkali is like. The H plus ion or the OH minus ion, in the case of alkalis, doesn't fully dissociate. It doesn't completely separate out. It only partially dissociates. So it's sort of available, but not completely available. So that's why something that is strongly acidic is much more reactive than something that is only weakly acidic, because it's got much more hydrogen available to react. Now, this is the idea of weak versus strong, but you can also have dilute or concentrated. So up here, you might have noticed this said weak but concentrated, strong but concentrated. So these are both concentrated. This one is weak because of this partial dissociation. This one is strong because of this complete or full dissociation. Dilute or concentrated is about how many particles there are in the water. So a good example of this is thinking about when you're making up some squash. You put the squash in, and if you put a little bit of squash, you get this kind of weak, slightly, you know, light-colored, pretty transparent drink out of it. And if you put loads of squash in a little bit of water, you get a really strong flavor and a much darker color. It's a great way of thinking about concentration. So if something's dilute, it has not very many particles in it. And if it's concentrated, it has lots and lots of particles in it. Now, I want to show you an example of why this matters. So here I've got a little tool showing battery acid. You can see the pH of my battery acid is at 1. Now I'm going to let it out so that I've got just a tiny bit of battery acid there. And I'm going to fill it up instead with water. Yeah, so we've got a tiny bit of water. We've got 0.03 battery acid at pH 1, and I'm going to fill it up to a litre. So we're getting about 300 times as much water as we have battery acid. But watch what happens to the pH. So you might think, well, the pH is going to go down hugely. Well, it does go down, but not loads. It's still a really strong acid. I've diluted this 300 times, so the concentration has gone way down, but it's still a strong acid, even though it's a very dilute acid. It hasn't got very many acid particles, but the acid particles it does have are completely disassociating. So there is a difference between something being strong and something being concentrated. A strong acid might be safe if it's very dilute. This might not actually have that much hydrogen knocking around. Still not a good idea to mess around with battery acid, but you get the point. A very concentrated thing, though, isn't necessarily dangerous if it's a weak acid. So having concentrated citric acid, some of you may have used that in cooking. You can buy it. It's perfectly safe. You can just eat it if you want because it's only a weak acid. It's very, very concentrated, but it's only weak. So we've got these two ideas which kind of compete against each other. The idea of concentration, about whether it's dilute, whether there's lots of acid there or only a little bit, and this idea of it being a strong acid or a weak acid, and that's a property of that chemical compound and how it's put together. Right, the final thing from me is a little bit more detail about the pH scale. So all of the stuff we've done so far, maybe your teacher went through in year 7, maybe that strong and weak stuff, and the dilute concentrated, maybe they didn't touch on that, and that might be new to you. This, again, this is definitely GCSE level, and so most of you probably haven't seen this before. This is looking in more detail at what's going on in the pH scale. So we talked about it, about H+ for acid and OH- for alkali. Let's start with pH 7. What the pH scale really is a ratio comparing how many H+ ions and how many OH- ions are available. And let's think about water. Well, water is H2O. It's kind of an H+ and an OH- put together. So for every H+ ion, you've got one H- ion. You can see in this picture here, I've got 10 red H+ ions and 10 blue OH- ions. The ratio there is 10 to 10 or 1 to 1. If we've got an even ratio of hydrogen and hydroxide ions, then that's neutral. If we start getting more hydrogen, then it starts being an acid. If we start getting more hydroxide, it starts being an alkali. So you can see up here, we've got loads of acid particles and just loads of hydrogen particles and just one hydroxide ion. That's an acid. Here we've got loads of hydroxide and just one hydrogen. That's an alkali. Now you might be looking at that and thinking, well, that's going to be a really strong acid there, and that's going to be a really strong alkali. Look how outnumbered they are. The thing about the pH scale is it's logarithmic. What that means is just one step on this pH scale, we're not doubling it or halving it, we're going up by a factor of 10. So remember we talked about it being a ratio? If I go from pH 7 to pH 6, all I would have to do is have, in this, I would have, if I take out those 9 blue dots, 1 hydroxide for 10 hydrogens. That would be pH 6. And go up another step from pH 6 to pH 5. Again, it's a factor of 10, so there'll be 10 times as many. This diagram here is actually the diagram for pH 5. There are 100 red dots, 100 hydrogen ions, and 1 hydroxide. So the ratio is 100 to 1. That's only pH 5. That's about black coffee. That's not dangerous. Yeah. So what the pH scale shows you is that it's logarithmic, this factor of 10. And something they might ask you to do is go, how many more hydrogen ions are there in this pH than that pH? So here's an example. If we look at moving from pH 4 to pH 1, so that's 3 steps, 1, 2, 3, you would go 10 times 10, 10 to go, there's 10 times more hydrogen to go to pH 3, 10 times again to go to pH 2, and 10 times again to go to pH 1. So 10 times 10 times 10, there are 1,000 times more hydrogen ions. And those of you who are maybe in the advanced and doing advanced maths might be much more familiar and just go, well, that's just 10 to the power of 3. That's easy. I've gone 3 steps. I do 10 to the power of 3. 10 to the power of 3 is 1,000. There are 1,000 times more hydrogen ions. The same is true if you go the other way, if you're going down into alkali. If you go from 8 to 10, you've gone 1, 2 steps. There are 100 times fewer hydrogen or 100 times more hydroxide ions. So this idea of it being a logarithmic scale means that each step you take, you're increasing or decreasing by a factor of 10. Right, that wraps up the bit that I'm going to do. So I'm going to hand over to Miss Wanstall, who is going to talk about some of the things.
What you do, sir, I've got the question, when do ions in acids dissociate? I've got what's a factor of 10, and I've got some confusion on what you've just gone through.
Okay, no problem. Let's start with the dissociate. So remember we talked about acids and alkalis forming H plus and OH minus ions when they dissolve in water. Like you can get a lump of citric acid and it's not actually very dangerous right now as a solid piece of citric acid. It's when you put it in water and then the hydrogen ions separate from the citrate, which is the other bit of citric acid, and then they become ready and available to react. They're not as ready and available to react in that solid state. So when you dissolve them in water, they separate, which are these pictures. So you can see here's ones which are partially disassociated. They haven't fully separated. These are ones that are fully disassociated, so that those hydrogens or hydroxide ions are completely separate from the rest of the things. So it's about, they will disassociate when they get put in water. To recap this, so the pH scale is a ratio. How many hydrogens are there compared to hydroxides? Let's go back to pH 7 and look here. I've got 10 hydrogen ions, 10 hydroxide ions. For each hydrogen ion, there is one hydroxide ion. They're in a ratio of 1 to 1. If I go to pH 5, each step on this is a factor of 10. That means I'm multiplying or dividing by 10. So if at pH 6, there will be 10 hydrogen ions for each hydroxide. I've got 10 times as much hydrogen, or another way of thinking about it, 10 times less hydroxide. So if I wanted to take this thing that's pH 7 and make it pH 6, either I could add 90 hydrogen ions, so I've got 100 hydrogen ions for the 10 hydroxides. That's in a ratio then of 100 to 10. Well, that's 10 for each, that's 10 to 1, 10 for each hydroxide ion. Or I could take out 9 of the hydroxide ions and just leave 1, and I'll have 10 hydrogen ions for each hydroxide. So I've managed to change it either by adding in 10 times as many hydrogens, or reducing down the hydroxides by a factor of 10, by reducing down 10 times down to just 1. If I go from 7 to 5, I've got to do it 10 times and then 10 times again. 10 times 10 is 100. I need 100 hydrogen ions for each hydroxide ion, which is what you can see in this diagram here. So if you went all the way up to pH 1, you have 1 million hydrogen ions for each hydroxide ion. Gives you an idea of just how potent those things can be.
And that might link into my next question from someone. Why does diluting it not reduce the acidity?
So you saw it did a little bit, but the reason that diluting it doesn't reduce the acidity very much is because of this idea it's a logarithmic scale. If I take you back to this window and if I set it up just right, then we should be able to show you this exactly. So let's go back to battery acid. Let's reset. Let's have some battery acid. Battery acid is at pH 1, and I have got 0. Let's have. What do we want? We want a no, 0.0. Let's have a tiny bit. We'll have 0.1. So we've got 100th of a liter. Yeah. So what I'm going to do is, it's at pH 1. I'm going to add 10 times as much water. So if we go up to 1 liter, and you can see the pH has gone down to about pH 2. We've added 10 times the volume of water compared to the acid. So we've now spread that acid out 10 times. We've got 10 times fewer acid H+ particles in there compared to what we had before. And the pH has gone down by 1. That's that factor of 10 again. I've spread out. So it does affect the pH, but you have to dilute it by a factor of 10 to get a change of 1 on the pH scale. And if I add even more water and we go up to a liter, I've now got 100 times the volume I had before. And you can see the pH has gone to about 3. So by having 100 times the volume of water, I've managed to move the pH 2 steps on the pH scale, because it's a factor of 10. So to move 2 steps is a factor of 100, 10 times 10. So I need to dilute it 100 times to make it, to lower the relative abundance of hydrogen in that solution. A good question though.
And last question I've got at the moment, is diluted and disassociated the same?
No. Remember, disassociation is about what does the individual thing do? How well does the hydrogen or the hydroxide separate? So these are fully disassociated. These are only partially disassociated. Dilute is about how many particles are there. If there's not very many particles, then it's dilute. Doesn't matter. These might be fully disassociated. There's just not very many of them. Whereas these might be only partially disassociated, but there's lots of them. So the concentration is about the number of particles. Dilute means not very many particles. Concentrated means lots of particles. That is completely separate from whether they dissociate. So here you can see we've got, these are both dilute, there's not very many particles, whereas these are both strong, there's lots of particles. These are both strong acids, they've fully dissociated. These are both weak acids, they're only partially dissociated. Now, if you look, you can see there's 2 hydrogens here ready to react. So even a concentrated weak acid may be less dangerous than a dilute strong acid. You see here there are 4 hydrogens available to react. So this might still be a more reactive, even though you've diluted it, because it's strong. Now, it depends exactly how dilute you make it and how concentrated you make this acid. A very, very, very concentrated weak acid could have more hydrogen available than a very, very, very dilute strong acid. So it's not always true that the strength is more important than the dilution. It's a factor of both to see how much hydrogen is available, which is what pH measures. Okay, Miss, I think you've got about 15 minutes if you want to talk them through the experiments you're going to be asking them to have a go.
Should we check if there's any more questions?
Oh, yeah. Any last chance? Any more for any more?
No. Okay. Okay. So I'm just going to share my folder. So there are a range of activities that we've put together, or I've put together, to give you a chance to maybe do some practical at home, as well as an activity that you can have a go at if you can't do practical at home. So there's some options. So this I've taken, it's from year 7, I'll be honest, but who doesn't like a bit of colouring in? Is basically my thought process on this. So this is just a pH scale for you to colour in. You could design your own, and then using the internet or your own knowledge, find some examples. And then at the bottom, there's another question which we haven't gone over today. So this could be a bit of a recap of what you can remember. So what is neutralisation and useful neutralisation reactions? So that is one option task there, colouring that in or designing your own pH scale. I don't know if anyone's got any questions on this task. I'm hoping this one's quite self-explanatory.
People are saying, is it compulsory to do the practicals? I would say no.
No.
If you don't want to do the practicals, then this is the task you should be doing.
Yeah. And I've also designed one of the practicals so that you can do it even if you can't do the practical bit, which I'll get on to. So you've got options this week is essentially where we're coming in from. Okay, so this is one task. As I said, this is like design your own or use this to make a lovely pH scale. And then we've got the famous red cabbage indicator practical. I've put 2 links in. Again, they have come from year 7 because you would have done this hopefully in year 7, but there is a method video and then a year 7 recap of the pH scale for you there. And then we've got a nice, oh, sorry, hang on. I'm just going to move my video boxes. Method laid out here as well. So the equipment you would need, it does say sensible adult. I do recommend having an adult around. I don't want anyone getting burned or hurting themselves while doing this. For this one, you would need some red cabbage to actually make the red cabbage indicator. And then saucepan, and then various things at home that you might have. So in your cupboards, not things like oven cleaner though. So stick to things like lime juice and vinegar, toothpaste, various things like that. Please be safe when doing these things. So the idea there is obviously you are going to make your own cabbage indicator. And then we've got the method that tells you how to do it. So chop your cabbage up. It does say get a sensible adult to do this bit. You're year 9, so I think you can sensibly chop cabbage. If you don't think you can, then obviously get someone to do it for you. You then put your cabbage in your saucepan, add water, and then boil it, and you should see a lovely colour change of the water to like a purpley colour. That you have then made your indicator. Let it cool down because you do not want to actually burn yourself on the hot indicator, and then add your substances to glasses like you can see in this picture, and it's up to you what you do and what substances, and then you can add indicator. And I've got a rough photo there just to show you some examples. And then tasks linked with this one, what were the variables? Because it's always important to go back to that. Design a results table before you do your experiment. So what are you going to test and what did you observe? And then evaluate your method. What could you maybe do better? And what could you do to make your experiment more reliable, precise? And then a little conclusion. And then I've put some questions on there for you about how is the cabbage different from universal indicator? How do you think this experiment would be different in a school laboratory? And then if you wanted to, on this task, you could do a poster or model of the pH scale, but I talked about that with the other task of the pH scale. So you could also, with this method, change the design of it so it's less wordy. You could do like a video of you doing the practical for year 7s if you wanted, a slideshow of photos, drawings. I'm trying to make it very creative, so it's up to you how you approach these sort of things. Does anyone have any questions on the red cabbage indicator practical idea?
So some people are saying, do we take a picture of this and submit it to the class? If they chose to do this, what would they submit, Miss?
So if you chose to do this, you've got options. As I said, I'm trying to make this very optiony. I hope it's not too optiony. So you can either go through these tasks here. So identify the variables, you could type them onto this document, design a results table and just type those answers. Or if you wanted to approach it differently, you could make a model of the pH scale, you could do a poster, or you could do a video of you doing the practical and submit that, or you could take some photos of the different stages and put them on slides or submit them. So it's up to you how you submit it and what you want to do. Essentially, I want you to enjoy what you're doing this week. So I don't want to say, you must do this.
Yeah, so some people saying what's compulsory. The compulsory things I would say is the Google form. That will that's not quite ready yet, so that will be going up in your classrooms shortly. And one other thing of your choice. So there will be a selection, a menu of tasks to do. You've seen 2 of them so far. Pick one of those and do that. Yeah, if you want to do more than that, then you're very welcome to. So do the Google form is mandatory, and one other task of your choice. So we've got practical options there, but there's this the doing the pH scale task, which Miss showed you first, if you don't want to get involved in the practicals.
Yeah, so there's options available. Any questions on the cabbage indicator method practical one?
No, I think that's good. If we move on.
That's task 2. And then we've got this one, which is task 3. And I picked this one because 1, I haven't seen this one done before. And 2, I thought you might actually be able to do this one at home with random food that you've got lying around. And also it's Pancake Day last Tuesday, so I figured most of us have got some lemon juice knocking around. So this is Why Do Apples Turn Brown, which I found perusing earlier. And this is to do with the acidity or using lemon juice, which is an acid. Now it says you can use an apple or a pear. I was thinking apple, pear, potato. You could have a range of foods that you could try this on. It could be interesting to sort of widen it out from just an apple or a pear. A knife, a little bowl so you can fit in half your apple, pear, potato, whatever you're doing, some lemon juice, a clock or a timer, some plates, a pen and paper, and help from adult if needed. So first thing you do is you make 2 labels, control and lemon. You see where we're going here, always important to have our control. And then we pour lemon juice so it covers the bottom of the bowl. And then we're going to have our control, which would have water in it. So, and then it says here, with adult help, cut the apple so it's in half, or your chosen food. Obviously, again, I do say if you can do that yourself, you can, but please don't chop any fingers off. And then this one, take half of the apple or whatever you're looking at and leave it in the lemon juice for 2 minutes. And then there's the other half without lemon. So you could either do that with water or just leave it on the side. So one with lemon, one without. And then observe the colour of both halves after 2 minutes, and maybe have a results table you've designed to say, or take a photo to see what's happened. And then after 10 minutes, observe them again and keep going for half an hour. You could leave it even longer if you wanted to. And what do you see at the end of it? Now, I know there's some photos there, but I'm going quickly. I've then included what happens. So it's the idea that the acid is actually a bit of a preservative, which is why I said you could try different foods to see what actually happens. You could also try different juices, as it says there. So lemon, lime, cranberry, grape, grapefruit, any of these things that you might have knocking around, apples, pears, potatoes. But essentially, it's a use of acids to preserve fruits experiment. And it might be something that's better than lemon. Is there any questions on this one?
People were asking about using limes, but I think you covered that.
Yeah, I think lemon or lime, you could try both, yeah.
Even orange juice, if you've got some fresh oranges, or I'm looking at my fruit bowl, I've got some tangerines, you could try those.
Yeah, it's just what you've got knocking around at home. I just thought it could be quite interesting to see. It's a nice one with timing, so being accurate on your timing, taking photos of seeing what happens. There you go. So that is experiment 3, fruit. And then last experiment, and this one I haven't actually given you that much because I thought maybe this would be a bit of a challenge one to design yourself. So this is to do with indigestion tablets. So Rennie's and Gaviscon's and cheap Asda's own or Sainsbury's own or whatever supermarket own. Not promoting supermarkets there. Indigestion, as you should know, is caused by the excess hydrochloric acid in your stomach. So indigestion tablets have been designed to neutralize that acid. The idea of this experiment is to investigate the effectiveness of those indigestion tablets, but you doing it on different types of household acids. So you can use glasses and bowls. Your antacid tablets, you could maybe use one and break it into 4, or you could use many. It's entirely up to you. And then different household acids. So I've put as examples water, vinegar, lemon juice. And then I've put, for this one, you can design your experiment to investigate the rate of the reaction of the antacid tablet with the different types found in the home. So again, variables, how are you actually going to lay this out? What are you going to do? What do you think will happen? So will the antacid tablet neutralize lemon juice more than water? Will you see more of a reaction in water than vinegar? Those sort of ideas. How are you going to record your results? So would you make a table? And then what conclusions can be made? And again, it's just a kind of play on this one. So putting your antacid tablets in the different solutions and seeing what happens and how fast it happens maybe. So that is experiment or idea 4. So you should hopefully, is there any questions on this one before I close it?
I think this might have applied to the previous one, but writing a summary of our results.
Yeah.
Is that something they should be doing?
They can do, or take photos and then say which one. Yeah, any of them really. A summary conclusion is always a good idea. I always think getting in the habit of writing a conclusion from results is good, as well as what could you do differently, what would make it more reliable, precise, accurate, blah, blah, blah. I don't know.
Yeah, and it's probably worth saying this last one is a little bit less well structured, and that's intentional.
Yeah.
In that we're giving you a bit more freedom to design your own experiment and explore. If that's something that you relish and you want to have a go at, then do this one. If that's something you're like, well, I don't know what I'm going to do, then maybe pick one of the others.
Yeah. Yeah, this one was the wishy-washy one on the grounds of you are triples, so I did want to give some of you that challenge of deciding, well, what are you going to change? I mean, it could be you wanted to change the amount of an acid tablet and keep one chemical the same. You know, this is where you can sort of really play around at home and see what you want to do.
So just as one's going back, Tally earlier asked about the colours on the pH scale and what colours they are. That links back to what I showed you before about the universal indicator. Often when you see that, when you're colouring in this, the ones to use, I would suggest, are the colours that universal indicator goes with it. So you can see here, the colour with universal indicator, with UI, that's what the UI stands for, universal indicator. Those are the colours that I would choose to use when colouring my pH scale, and that's why I would choose those colours. Okay, any more questions about anything so far? So just to recap, what we're expecting from you is you do the Google quiz. That's not quite ready yet. That will be going up into classrooms probably in about an hour. So after lunch. And have a go at least one of these. There's things you can do there if you don't have any equipment at home. There's still things you can do, but if you want to do more than one, you're very welcome to. But so all of these will look optional, but we would like you to definitely do the Google quiz and then choose one of these, at least one of these, to have a go at. If you have any questions or any problems, do let us know. And last chance to ask any final questions. Those of you saying thank you, you are very welcome. And now, if you don't have any questions, I'm going to stop recording and you're very welcome to leave. If you do have any questions, we'll stick around for a little bit longer for you to ask those questions.
I'm just going to answer the question, Spuffy.
I don't understand that.
Angel's too mopey, but ideally I think she should have been on her own, and I'm glad you didn't ask about Riley.
Oh, okay, I now understand that question. Gotcha. Yeah, I'm totally Team Spuffy.
I'm Team Spuffy. I met James Masters, he's a legend.
Okay.